So I wanted to do a quick video on just solving exponential and logarithmic equations. There are a couple of different strategies that we're going to use. So we'll use solving exponential equations if they have like bases, or if we can make them into like bases. We'll be solving exponential equations where we use logarithms, and then we'll also solve some log equations where we use our log properties first. Okay, so first, exponential equations using like bases. So the one-to-one property of exponents is like this. If a to the m equals a to the n, then m equals n. So here we go. The first one, I have e, so our natural base e raised to the 5x minus 1 equals e raised to the x plus 3. The bases are the same, which means the exponents are the same. So we can say when this happens that the only way for this to be true is if 5x minus 1 equals x plus 3. And there we go. So then we would solve this equation right here. So subtract x from both sides, add 1 to both sides. So I'll get 4x equals, what is that, 4. Oh, so x equals 1, right? Divide both sides by 4. So this equation is true when x equals 1. Now, you could also have solved this one by taking the natural log of both sides. So there was an option. Okay, second question, I have 4 to the x equals 32 to the 7 minus x. This one's a little bit trickier. They aren't the same base. And maybe you're thinking, oh, but if I multiply 4 times 8, yeah, also a good thought. But when we're doing exponents and logs, we need, right, think of that base and a power. So I don't want something multiplying it. I want something raised to the. So what is something that could be raised to something, right, to get us to the 4 and the 32, right? So all of that, right, you guys are saying 2. So 4 is the same thing as 2 squared, so we're going to make that swap. And 32 is the same thing as 2 to the 5th, so we'll make that swap as well. So 4 is the same thing as 2 squared to the x equals 32, which we know is the same thing as 2 to the 5th, and all of that is raised to the 7 minus x. Okay, now they have the same base. So let's just do, right, we'll use an exponent property here from, right, a previous algebra life. So powers to powers we multiply. So on the left we would get 2 to the 2x equals, and then on the right, 2 to the 5 is going to multiply the 7 minus x. So 5 times 7 minus x. Come up here. So 2 to the 2x equals 2 to the distribute, what is that, 35 minus 5x? Make sure, yes, okay. Like bases, finally, there we go. So that means if these are the same, that our exponents have to be the same. So 2x must equal 35 minus 5x. So add 5x to both sides, so I'll get 7x equals 35, divide both sides by 7, so x equals 5. It never happens that I get integers when I make this up. This is so cool. Nice. Okay. So if you can make them like bases, try to do that. If you cannot, right, if you don't have two equations with exponents in the, or with variables in the exponent position, or, right, the bases are just totally different, then what we're going to do is use logarithms. So on our first one, I have e to the 9x plus 1 minus 7 equals 3. So the first thing we're going to want to do is isolate, if we can, isolate the term with the exponent. Okay, so I want to get this e to the 9x plus 1 all by itself, so we're going to start by adding 7 to both sides. So now I have e to the 9x plus 1 equals 10. Okay. So now to get this 9x plus 1 down in front, what we're going to do is apply the log of the same base as the base in your exponent. Remember, they are inverse functions of one another. Exponents and logs are inverses, so they cancel each other out. So this is, right, base e, so I would do log base e, which we write natural log of both sides. Natural logs, right, logs apply to something, they always go on the left, right? Their argument, what you're taking the log of, goes on the right. So the natural log and the e cancel. We get the 9x plus 1 equals the natural log of 10. And now we're going to solve for x. So isolate, take the log of both sides, whatever base you have to use, okay, and then we do the solve what's left. Okay, so we would add 1 to both sides, so 9x, subtract 1, thank you. So 9x equals negative 1 plus natural log 10. I'm not going to do anything with that natural log 10. It's going to stay that until I grab a calculator and do an approximate answer. Okay, so we're going to leave it as is. So I know, I'm sorry, I didn't space well. So divide everybody by 9. I'm going to tilt sideways, sorry. Dividing everybody by 9 would give me x equals negative 1/9 plus 1/9 natural log 10. Okay, there are a couple of different ways you can write that. Natural logs, well, logs in general are kind of funky that way, in that there are multiple ways to use your log properties to manipulate how it can look. So this is just one way it could possibly be. Okay, so this would be our exact answer, right? Has all of the information in there. Now, if I wanted an approximate answer, so we'd use our squiggle equals. I'll go ahead and grab a calculator. Let's see, how would I want to do that? I think I'm going to do this first part. I'll do it in a couple steps. I'll do negative 1 plus natural log 10. So negative 1 plus, where's my natural log? Here we go, natural log of 10. I'm going to hit enter and then divide that by 9. So my approximate answer would be 0.1447. So x is approximately equal to 0.1447. All right, now the next one, our bases, right, are not the same. You're thinking, oh, but it's just off by 2. Yeah, but by a factor of 2, I can't do exponents and get there, right? I can't get from 3 to a 6 with an exponent. There's nothing smaller, right, to break those down into. So instead, we're going to apply the log to both sides. So now a question would be, well, which log do we use? And the answer, it's not very satisfying because it's well, you can pick one, right? There might be a better choice. So maybe you'd say log base 3. I don't know. I think I'm going to go with a log base 10 or a log base e just because they're on my calculator. If you did a log base 3, you would, right, end up using a change of base property anyway to get your approximate answer. So I'm just going to go log base 10, a common log to both sides. So I'm going to take the log of 3 to the x minus 2 equals the log of 6 raised to the 2x plus 5. Okay, doing the same thing to both sides, log base 10, so totally legal. Now if I use my exponent property of logarithms, those powers, right, can come down in front. Log base 10 of 3, that's just a number, right? It's going to be a big decimal number that I don't want to write. So if I just leave right, log base 10 of 3, log base 10 of 6, that contains all of that information. So now I have x minus 2 times the log of 3 equals 2x plus 5 times the log of 6. Notice where I put my parentheses, everybody. Right, those things that came in front are binomial, so I want to make sure they get distributed as needed. So go ahead and distribute your coefficient logs. It feels weird. It's just a number written right this way. So I'm going to get x log 3 minus 2 log 3 equals 2x log 6 plus 5 log 6. Take a deep breath. Find your terms with variables in them. Those are going to go on one side. Terms without variables in it going to go on the other. So I will I'm going to put my x's on the right, so I will subtract x log 3 from both sides. minus x log 3. I'm writing it under. They are not going to combine. They're going to stay separate for now. I'm going to also grab a separate piece of paper because, of course, I didn't leave myself nearly enough room. I'm sorry. You guys probably are able to write smaller than I am. So I'm just going to take a regroup step. So now I have negative 2 log 3 equals 2x log 6 minus x log 3 plus 5 log 6. Sorry, with me? Okay. So now my 5 log 6 has to move. So I'll subtract 5 log 6 from both sides. Okay, another regroup then. So now I have 2x log 6 minus x log 3. And then on my left side, I have negative 2 log 3. Are those really both negative? No, I don't think they're both negative. Oh, I guess they are. Okay. Okay. Minus 2 log 3 minus 5 log 6. We're going to factor the x out of both terms on the right. So x comes out. I leave behind 2 log 6 minus log 3 equals negative 2 log 3 minus 5 log 6. And then divide both sides by 2 log 6 minus log 3. 2 log 6 minus log 3. Cancel over there. So our final exact answer, negative 2 log 3 minus 5 log 6 divided by 2 log 6 minus log 3. Oh my gosh. Now, catch your breath. Think about your log properties. Everybody has the same base here. Everybody has base 10, right? So, there are a bunch of different ways we could write an equivalent expression here. An equivalent exact expression. I'm not talking about grabbing our calculators and coming up with a decimal, which we can do, right? I'm talking about different exact answers, right? This negative 2, boom, we could pop that up on top of the 3, right? It could be the power of the 3. Same with the 5, same with all of these, right? I have the difference of 2 logs. I could do something with that, right? Yeah, so there's a whole bunch of different ways we could write equivalent expressions, so you're going to want to be careful on those. All right, I'm going to skip the finding an approximate answer on your calculator, just for time. Okay, so now let's solve a log equation. Okay. So we're going to use those log properties, and we're going to get a single logarithm, and then we are going to, so the verb I use is exponentiate. Exponentiate. Okay. So we're essentially going to do to change your log equation into the exponential equation version, right? Do the little loop-de-loop. Okay, so we're going to do that after we get a single log on one side. So on our left here, I have a log of x plus a log of x minus 21. So same base, both base 10. So the sum of 2 logs is the log of the product. So I'll have the log of x times x minus 21 equals 2. Okay, so now we have 1 log equals a number. So this base is 10. So if you want to write that in there to be extra sure. So our base, and remember the loop-de-loop, so the base, to get to the exponential version, 10 to the second equals, write that argument. Now I have an equation that doesn't have logs in it. Awesome, right? We're back on a much more familiar setting. So how would I solve this equation? Well, let's see. I want to get rid of the parentheses. So and maybe we'll square. So now I've got 100 equals x squared minus 21x. Oh, I have a quadratic. Great. We have strategies for solving quadratics. So we'll try to factor maybe. So I'll subtract 100 from both sides. So x squared minus 21x minus 100. Or write quadratic formula, whatever your strategy of choice is. I made it up and I made it so hopefully it factors. if I hopeful factor here, if I wishful factor, call me on it later. So multiply to negative 100. I think it's 25. I know it's 25 and 4. So negative 25, positive 4. That'll get me my negative 21. So x minus 25 equals 0. So x is 25. Or, right, same thing with my other would lead to x equaling negative 4. Now, with logarithms, remember, we can only take logarithms of positive numbers. Right, there is a big domain restriction on logarithms. So we just need to make sure, so we must make sure our answers, our solutions, are in the domain. And I hear you, you think, oh, well, you've got a negative 4, that's not there. Well, but maybe sometimes it will, right? So just because the value you get is negative, there might be some things happening to the x inside of your equation, right, that would lead it to be fine. Okay, so we're going to check the negative 4 because that's the one, right, that's the most concerning. So that would lead me to the log of a negative 4. Okay, you're right, it doesn't work. I can't use it because it's not in the domain. So we'd toss the negative 4. Let's just make sure the 25 will work. So log of 25, yeah, we can do that. Log of 25 minus 21. That still gives me a log of a positive number, so we can keep that one. So 25 is good. Oops, sorry. Okay, one more. So log base 2 of x plus 3 minus log base 2 of x minus 1 equals 3. So the difference of two logs means we make a ratio out of their arguments. So log base 2 of x plus 3 over x minus 1 equals 3. Okay, so we're using our log properties to get one logarithm, and we're there. And now we're going to loop-de-loop it. So the base raised to the third equals the argument, so 2 to the third equals x plus 3 over x minus 1. What's our next strategy? So maybe, right, you can be thinking different things at this point in your algebraic career, right? You have different tools depending on who, right, who you learned from. Maybe you see cross multiply, maybe you see multiply by the LCD. Either way, right, I'm going to get that x minus 1 out of the denominator. So if we multiply both sides by x minus 1, we'll take this 2 cubed and turn that into an 8, equaling x plus 3. Distribute your 8. So 8x minus 8 equals x plus 3. Kind of just, right, I always think of this as the clearing everything out of your closet first. So, right, lay it all out, see what you're going to keep before you put it back in. So here's everything we have. It's linear, which means all our x's go together. So subtract x from both sides. Let's see, add 8 to both sides. 7x equals 11. So it looks like x equals 11 sevenths. Okay, let's take a quick look. We're going to check it in our, right, our two log terms, make sure that it's allowed. So 11 sevenths plus 3, that'll stay positive, good. 11 sevenths minus 1 will also stay positive, also okay.